When a number is written as another number greater than or equal to 1 but less than 10 times an integral power of 10, that number is said to be written in scientific notation. And here's an example. 9.3 times 10 to the 7th. The 9.3 is greater than or equal to 1, but it's less than 10. And the 10 to the 7th power is an integral power of 10 because 7 is an integer. The 9.3 is called the mantissa, and the 7 is called the characteristic. When we multiply it out, we get 93 million, which happens to be an approximation often used to represent the number of miles that the Earth is from the Sun. Let's try to figure this out without using a calculator. We start with 9.3, we're multiplying by 10 to the 7th. Well, you probably already know that if it was 93 times 10 to the 7th, you'd simply add 7 zeros. You look at the exponent, the 7, it's the key. But since it's 9.3 instead of 93, instead of simply adding 7 zeros, what we're really doing is moving the decimal 7 places. So we've already moved it 1 to get it around the 3, 2, 3, 4, 5, 6, and 7, and then I add in zeros as necessary, which you can see requires 6 more to get that decimal moved from 9.3 to where it belongs in 93 million. And of course, in 93 million, since there are no significant places to the right of the decimal point, the decimal does not even have to appear in the number. Here's another number. This is often used to represent the number of feet that light can travel in a second. 186,000. And what we're going to do with this number is start with 186,000 and convert it into scientific notation. Well, we know that in scientific notation, we want the decimal to go between the 1 and the 8, so we end up with a number that's greater than or equal to 1 but less than 10. So that's where the decimal is going to end up. And then we have to remind ourselves where the decimal was in the original number. Well, it was to the far right. Of course, you can't see it. We don't need to write the decimal in 186,000. But when we start to count to find how many moves from the original decimal to where we're going to place it, we start on the far right. There's 1 move, 2 moves, 3, 4, and 5. So it's going to take 5 moves to get from the far right in 186,000 to between the 1 and the 8 in 1.86. So now we write 1.86 times 10 to the 5th power because we moved that decimal 5 places. The number at the bottom is said to be written in scientific notation. Here's a very small number. Very small numbers can also be written in scientific notation. For this one, we're going to want the mantissa to be 1.32. Well, now we can see both decimal points, the one in the original number and where it's going to be when we put it in scientific notation. And our job is to find out how many places are in between those 2 decimal points. So let's count. We make some marks as shown, and then we count them up, and I count 9. So we're going to have to move the decimal point 9 places. And our mantissa is 1.32, but of course this is 9 places in the opposite direction from when we were putting large numbers in scientific notation. So of course, for small numbers, it's a negative exponent. 1.32 times 10 to the negative 9th. And now let's take a very small number that's already written in scientific notation, and let's see if we can write it in its original form. We write the 4.213 way over on the right because we know it's a small number and we're going to need zeros on the left side. We start our first move, but of course the exponent is negative 11, so we're going to need 10 more moves, and there they are. Now we're going to count to make sure we've made 11 total moves. We put in the new decimal point, we fill in the zeros, and it's customary then to write 1 more 0 on the left side of the decimal, not required but customary, the one with the blue arrow, and there's our number. It's a decimal point, 10 zeros, and then 4213, a very small number. At the top it's in scientific notation, and at the bottom it's written in what's called standard decimal form. Now let's multiply 2 numbers that are written in scientific notation. Sure, you can get out a calculator and type the whole thing in, but Sometimes typing that in is more complicated than some of the shortcuts we can use. Well, let's put the powers of 10 together and then the two mantisses together. And the powers of 10, of course, make 10 to the 12th. And I am going to use a calculator for 4.21 times 3.4. And I get 14.314. And it's almost in scientific notation, except for the 14.314 isn't between 1 and 10. So I'm going to have to make one move of the decimal. And in doing that, I get 1.4314 times 10 to the first is equal to 14.314. And now I have 10 to the first times 10 to the 12th. I've made an adjustment. And in scientific notation, I get 1.4314 times 10 to the 13th. But that's not my final answer, because the accuracy of scientific notation is only good as the least precise number. And when I say least precise, the two numbers circled at the top. One is rounded to the nearest tenth, and the other is rounded to the nearest hundredth. We say rounding to the nearest tenth is less precise than rounding to the nearest hundredth. So our final answer only needs to be rounded to the nearest tenth. And there it is, 1.4 times 10 to the 13th. The number of digits in the mantissa is called the number's significant digits. The answer of an expression involving two or more numbers in scientific notation is no more accurate than the number with the least number of significant digits. Round off only the final answer. Here's another one. Again, one of the numbers is to the nearest hundredth, one to the nearest tenth, but let's not round yet. If we round too early in our expression, we might get what's called round-off error. So we're going to multiply these two numbers and then round off to the tenths place, because the 3.4 is only accurate to the tenths place. Once again, we use the commutative property to get the mantisses together and the powers of 10 together. The powers of 10 make 10 to the negative 12. We've already looked at these two mantisses, 14.314, but now we have to write 14.314 in scientific notation. One move to the left, so we get 1.4314 times 10 to the first is equal to 14.314. And then to finish, 10 to the first times 10 to the negative 12 is 10 to the negative 11th. Now we can round off 1.4 times 10 to the negative 11th. We have now found the product of two numbers written in scientific notation. We've written that product in scientific notation, and we've rounded it off to the correct number of significant digits. And now we're going to find the quotient of two numbers written in scientific notation. From what we know about fractions, we can find the quotient of the two mantisses and also find the quotient of the two powers of 10, and then find the product of those two quotients. Well, again, I'm going to use a calculator to get the quotient of the mantisses, and I'm going to use my rules for exponents. 5 take away 13 is negative 8, so I get this long number, 0.29645 times 10 to the negative 8. And in fact, when I use my calculator filled with numbers on the screen, and I don't want to round off too soon, but I did need to cut the number off somewhere because the numbers just filled the screen, and I knew that they weren't all significant. So for now, the top mantissa, 2.176, is to the thousandths place. So I wrote two extra digits so that I wouldn't have a round-off error. That's why I ended up with 0.29645 times 10 to the negative 8. And then, of course, I want to make my mantissa between 1 and 10, so I'm going to move that decimal around the 2 to make 2.9645. And in order to do that, I express that number in scientific notation. So I'm going to make the adjustment. And now I'm ready to do two things. I'm going to combine the 10 to the negative 1 times 10 to the negative 8 to get 10 to the negative 9th. And I'm also going to examine my original two mantisses. One was to the nearest thousandth, one to the nearest hundredth. So my answer has the significant digits to the nearest hundredth. So I've now rounded off my mantissa to 2.96. And I've rewritten my power of 10 as 10 to the negative 9th. And there's my number in scientific notation, the quotient of two numbers that were originally written in scientific notation. Once again, if a number x is written as a number n such that 1 is less than or equal to n, which is less than 10, multiplied by an integral power of 10, then the number x is written in scientific notation. It is used for both very large and very small numbers.